In this example, you're asked to solve a homogeneous system of linear equations here. The defining characteristic for a homogeneous system of linear equations is that your constant column here, so the constants are all equal to 0. The way that we solve it is the same method that you've been using for solving systems of equations since the beginning of this course, which is to start by setting up an augmented matrix where the first row would be 1, 2, negative 1, 0. Okay. I'll try to write this fairly neatly. I already kind of failed in row 2 there, but okay. Now, in row reducing, we start in the top left corner, work your way down towards the bottom right. And as you go work through the matrix, we go column by column. So we focus on the first column first. This thing already has a 1 on top, so what we'd like to see are zeros below it. So I'd like to see this negative 3 here become a 0, and also the negative 1, but I'll focus on one operation at a time here. So in order to get a 0 in that position there, row 2, column 1, we have to think about what row operation would work well. If you're following kind of the standard pattern for these row operations, then probably what you'll come up with is 3 times row 1, which will give you 3, plus row 2. And that'll zero out that entry right there. So actually, I'll write this in black. So first row operation I'm going to apply is 3 times row 1 plus row 2. So row 1 is going to stay the way it was. Now, if you're having trouble thinking through these row operations, then you have the option, and this is optional, but you have the option of writing out scratch work. And a nice way to organize that is to write, okay, 3 times row 1, 3 times row 1 plus row 2, right? That's going to be the new row 2. This is the row operation that's planned. Okay, so we write out what each of these refers to. So 3 times row 1, here's row 1, so this will be 3, 6, negative 3, 0. Okay, plus row 2, which is negative 3, negative 1, 1, 0. So now add those together. So 3 and negative 3, 6 and negative 1, negative 3 and 1, 0 plus 0. Okay, so that's the new row 2. Okay. Now, I could, if I really wanted to do one row operation at a time, then I could just copy down row 3 the way it is. And then the next thing that we would do is focus on row 3 here and getting a 0 in this position. Because that row operation is independent of, so if I do 3 times row 1 plus row 2, put that in row 2. I could also do, I'm going to pile this on here, just 1 times row 1 plus row 2. Just row 1 plus row 2 will zero out this entry here. I'm sorry, I said 2, I meant 3. Okay, so row 1 plus row 3 will zero out this entry here. Okay, so that's 1 plus negative 1, 2 plus 3, negative 1 plus negative 1, 0 plus 0. So it turns out when you do that row operation, you get the same result that we got in row 2. When you notice that 2 rows are equal to each other like that, then you know that one of those rows is just going to zero out. When one row is just a multiple of another row. So in this case, well, let's look at it this way. Column 1 is all fixed up the way we want it, 1, 0, 0. So you move over to column 2. I know that typically we would focus on, okay, I want to make this entry right here a 1 right now. But you have the option, if you want, to just leave. Your pivot is, by definition, a non-zero number. It doesn't have to be a 1. So at least for now, we could leave it as 5 and then just get a 0 in this position below it. So that would still get us towards echelon form for this matrix. And see, it's convenient to leave this entry as a 5 then, because then we could just do negative 1 times row 2, add that to row 3. And that'll give us -5 plus 5, so it'll give us a 0 in this position here. Okay, so again, though, when you perform these row operations, one of the key things is just make sure you copy the matrix, copy the entries here correctly. So just be real careful, because when you lose a negative or something like that, things go downhill real fast. Okay, so 0 plus 0, -5 plus 5, -1 times this would be 2 plus -2, and 0 plus 0. Okay, so there's our new matrix. And like I said, I mean, you can assume that that's going to happen as soon as you see that one row is just a constant multiple of another row. Okay, so we're trying to solve the system. This is actually in echelon form at this point. The row of all zeros is at the bottom. The pivots go down and to the right of the one above it. So we could stop here and start writing our solution set. However, notice that there's a free variable. So because this third row zeroed out like that, that means we're not going to get a pivot. We're not going to be able to get a pivot in column 3. So since you have one of these variable columns without a pivot, then we know that x3 is a free variable. Guess I'll put variable here. So this thing has infinitely many solutions. It's a dependent system. I'll write that here as well. Okay. So this system of equations has infinitely many solutions. When you're looking at a dependent system, and this is my personal preference, but I'll go ahead and advise you guys to do the same. If there is a free variable, infinitely many solutions, then I tend to prefer to reduce it all the way to the row reduced echelon form, the RREF. I tend to, and this is just my habit, if it looks like there's a unique solution, then I might just do echelon form and then the back substitution to find the values. But if there are infinitely many solutions, then I want to get this thing as reduced as possible to write out that solution set. Again, just personal preference. But so if we do want to go all the way to the row reduced echelon form, then we do want to make all the pivots 1s for one thing. So deciding what color to use. So now I would want to make that entry a 1. That's one thing that we need to do to get it to the RREF form. And the other thing is every column that contains a pivot has to have 0 everywhere else. So here's one of the pivots. This column does have 0 everywhere else, so there's nothing to worry about there. Here's your other pivot. So the other thing we're going to have to take care of is to get 0 up above in this position where the 2 is. But we should do that separately, one thing at a time here. So first make that a 1. Typically, if you want to take a non-zero entry and make it a 1, then we just multiply that whole row by the reciprocal. So the reciprocal of 5 is 1/5 times all of row 2. And so the new matrix there, so we're not changing row 1. Row 2 will be 1/5 times 0, 1/5 times 5, 1/5 times -2, so that's -2/5, and 1/5 times 0. And then the last row is already all zeros. Okay, so we're closer to the reduced row echelon form. One thing left is with your pivots, not only do you want zeros below, but you also want zeros above if you want to go all the way to the RREF form. So we need to make this a 0. That's the last thing we have to do, and then this thing's completely reduced. So in order to make this entry a 0 here, I would do -2 times row 2, so that'll give us -2 plus row 1. So -2 times row 2 plus row 1. So only row 1 is going to change this time. I'm going to get rid of some of this writing here. So row 1 is going to stay the way it was. So that was 1, 2, -1, 0. Oh, no, it's not. Yikes-a-rama. Sorry, guys. and I don't edit video, so sorry about that. Okay, anyway, -2 times row 2. Let me copy row 2 so I have it close by. And while I'm at it, just row 3 is all zeros. Okay, here we go. -2 times row 2. So -2 times 0, so that's 0. Oh, row point here, 0 plus 1. So that's 1. -2 times row 2. So -2 plus 2, that's 0. That was the whole point. -2 times this will give us +4 over 5 plus the -1 here. So I'll do some scratch work up here. So we have -2 times -2/5 plus what's in row 1, which is -1. So -2 times -2, this is +4/5 minus 1, which is 5/5. So this is -1/5 right here. And then, I guess I'll write that there. And then -2 times 0 plus 0. Okay, great. So there's the RREF form for this augmented matrix. Okay, so now we want to write the solution set, and this is something that we want to focus on in this section. So we reduced it all the way to this form. So if I write the corresponding equations, row 1 gives me this equation: 1 times x1, 0 times x2, minus 1/5 times x3, which is our free variable, equals 0. 0 times x1 plus 1 times x2, minus 2/5 times x3, which is our free variable, equals 0. x3 is our free variable. So that means x1 is equal to, let me do this right now. So when you have a free variable, we tend to like to set that free variable equal to a parameter. Commonly we use r, s, or t as parameters. Let's use t. So let x3 equal t, because I'm pretty sure that's what I used when I typed the solution. If x3 equals t, then x1, if we bump this over, equals 1/5 times x3, which we're calling t. We're setting x3 equal to the parameter t. With this equation, x2 equals 2/5 times x3, which is t. So now we can write our solution set, x1, x2, x3, any solution x to that homogeneous system of equations. Looks like this: x1 is equal to 1/5 times t, x2 is equal to 2/5 times t, x3 is just equal to t. So you can factor out that parameter t and write it this way. So the solution set in this case is all scalar multiples of the vector 1/5, 2/5, 1. It's all multiples of that vector. Which leads me to just one more thing I want to point out. So sometimes when you look at solution sets to these systems, you'll see it expressed as integers, or as multiples of a vector with integer entries. Just looks a little nicer. If we're talking about all multiples of this vector, then it's okay to replace this vector with some other multiple. Like if you multiply everything here by 5. So 1, 2, 5 would work. I guess if you want a kind of a formal way of how am I doing that, t, remember, represents any number. So if we want, we could have t equal, let's say, 5 times s. So if you replace this t with 5s, if s is any number, then 5s still just represents any number. So this still represents all multiples of the vector 1/5, 2/5, 1. But if I call it 5s and then distribute the 5 in here, then this becomes just s times the vector 1, 2, 5. It's fine if you, there's no rule that says you can't use fractions as your entries. when you're describing your solution set. So it's fine to leave it like this. But you'll see in a lot of textbooks, they'll translate that to the set of all multiples of some vector with integer entries, just to clean it up a little bit. So either of these solution sets describes the set of all solutions to that homogeneous system. So whether you express it as t times 1/5, 2/5, 1, where t is any number, or just some other parameter, let's say s times any multiple of that vector. So in this case, I did 5 times that vector.